Okay, today I'm going to talk to you about cylindrical coordinates. And this is a different coordinate system from, the traditional rectangular x, y, z. It's pretty similar to polar coordinates, which is something that we looked at in Cal BC last year and you hopefully looked at in the pre-calculus class. Except, we're going to expand out into 3 dimensions. You're probably going to watch me do this and you're going to be like, wait a second, where's the calculus? I have no derivatives, no integrals. This is the type of thing that is going to make some integrals later on in the course much, much easier to compute by hand. And so I'm just going to kind of tell you about this coordinate system and the spherical coordinate system so that when the time comes to take those integrals, they're much less unpleasant. I don't have to tell you about the coordinate system while I'm telling you how to change variables. So I'm going to start with the definition of our cylindrical coordinates. So let P be a point with coordinates x, y, and z. So I'm going to put that on my. This is going to be point P. All right. So r and theta, we're going to use r and theta again. And r and theta are going to be pretty much exactly like they were before, except that r is not going to actually be the distance from the origin. It's going to be the r theta in the sense of in the xy plane. So what I'm going to say is that r theta is the projection of P onto the xy plane. And then we're going to have a third coordinate, which is just going to be our height, okay? And then that's going to mean that z is, really the consequence is z is the same as z in rectangular coordinates, but we're going to say z is the signed distance from r theta, the point in the xy plane, to the point P. So z is, when I say sign difference, I mean, if it was below the xy plane, then this z would be negative like you would expect. Not difference, that's going to be distance. Okay, so what if I'm going to my goal here is to cook up the formulas for how to get from rectangular to cylindrical and cylindrical to rectangular. So I'm going to start, drawing my diagram. So I've got my point P, and the r and theta coordinates are going to be, the projection of P down onto the xy plane. So I'm just going to say, suppose that when I do that, I'm going to land right here. Well, then that's going to be right here, just in the usual polar coordinate sense. That's going to be theta, and that's going to be r. And then this distance here will be z. And so I think it would be pretty easy to see, okay, the x coordinate here is going to be just still r cosine theta, and the y coordinate is still going to be r sine theta, and that z is going to be z. Okay, so I'm going to actually just write that. X equals r cosine theta, y is r sine theta, and z is equal to z. And if we had r theta and z, and we wanted to go back into, if we had x, y, and z, and we wanted to figure out what r and theta were, and z was, I could say that, well, r is going to be the square root of x squared plus y squared, assuming that r is positive, right? Just like in polar coordinates, we could let r run negative back on the other one, but for the most part, I'm just going to assume r is positive. And then, really this comes from r squared is x squared plus y squared, which maybe I should have written, but, and maybe I'll write this one implicitly, that tangent of theta is equal to y over x, just like it was in polar. And then, okay, if I had z and I wanted to get z, well, I know that z equals z. Okay, so I'm happy to. All right, so what I'm going to do, I'm going to just talk about an example of a particular point P. That looks like it could potentially be interpreted as 1, 1, 1. So let's just say, suppose the rectangular coordinates of P are 1, 1, and 1. Let's find the cylindrical coordinates of them. Okay, so if P is the point 1, 1, 1, then in cylindrical, okay, remember it's R, theta, Z. So R is the square root of x squared plus y squared. Okay, that's going to be the square root of 2. Theta is going to be, well, you can think at 1, 1, if we just went straight down at 1, 1, we would have, that's basically pi over 4, right? It's not exactly 1 unit away, but it is going to be at that pi over 4 angle. And then Z is Z. So, okay, that's easy enough. But what if I, chose a different point Q and gave it to you in cylindrical coordinates, and, how we get them back in rectangular? So maybe I'll draw over here a point Q. And let's see, where do I want this to come up to? All right, I want it to come up to about right here. All right, and suppose the coordinates of point Q are 2, negative pi over 3, and negative 2. And so 2, negative pi over 3, and what did I say? Negative 2. Okay, if I'm trying to find the rectangular coordinates of this should be pretty easy. I'll start with the easy coordinate, right? Z is going to be negative 2 because Z is equal to Z. Okay. For x and y, I'm 2 units away along this negative pi over 3 track. Okay, so cosine of negative pi over 3 is positive half. Okay, so this will be 1. Sine of negative pi over 3 is going to be negative root 3 over 2, so I double that and I'll have negative root 3. And then I'll have my rectangular coordinates for point Q. Okay, so, going back and forth, points-wise, pretty straightforward. I would tell you that I trust y'all's algebra skills enough that you would be able to go back and forth on the equations to write an equation in rectangular form, convert it to cylindrical, do the reverse. I don't think that's going to be a major problem for you. So what I think I'm going to do for the rest of this video is I'm going to just kind of point out some surfaces in space that we are somewhat familiar with and look at their rectangular coordinates versus their cylindrical coordinates. And I think you will find that, for some of these things that I'm choosing, you could see that this is actually a kind of a simpler expression, which would make it easier to integrate over, because we know that integration in general is somewhat tricky and, best as possible, where we're headed, we're going to be integrating over regions or eventually surfaces in space. And so, finding a way to express those simply is going to make our life much easier. I imagine last year in the AP Calculus class you found that integrating with polar coordinates was kind of an annoyance. But in this class, it's a convenience. It makes difficult integrals much, much easier. Okay, so I think I'm going to maybe clear out some of this and just draw you some pictures. All right, so the first one I want to talk to you about is a cylinder. That would make sense. This is cylindrical coordinates. Okay. Let's see, maybe I'll draw in my axes. And, okay, this is going to be a cylinder with some kind of radius. The eraser. We'll be assuming that this is, centered around the origin in some sense. Okay. And I've got myself a cylinder, and I am assuming that this cylinder is extending vertically. Really, this is, any cross section of this thing's going to be a circle. And so what I'm going to say is that this is just the kind of the set of all points x, y, z, for which x squared plus y squared is the radius squared. And, just say for sake of example that that's 5, okay, then the rectangular equation for this thing is going to be x squared plus y squared equals 25. Pardon me. Okay. And I just erased it, but we know that the conversion factor for x squared plus y squared, that's r squared. So I'm going to say r squared equals 25. And then I could, simplify this and say that that means that this is the surface defined by r equals 5, where theta can be whatever it wants and z can be whatever it wants too. Okay, I could have said this is r equals -5, but if you think about how the polar coordinates works with negative r, it's the exact same points, right? Just with kind of the opposite notion of theta. So that's a cylinder. Okay, what about a paraboloid? That's something that we've talked about a lot in this class so far. Okay. It looks like a parabola that's been rotated around the z-axis. So what I'll do, I'll give myself the z-axis, x-axis. I won't need any negative area because I'm just going to have it start at the origin and kind of go up from there. So I'm going to draw myself a parabola. And then I'm going to give it some some 3D-ness. And so I'm going to actually probably, I don't want that much. Yeah, that'll be good. And I'll just kind of make it go around here. And then maybe I'll do some erasing. Okay, that's a problem. And what we saw is that this is like something similar to z equals x squared plus y squared. I mean, we can adjust this in various ways. We could, divide this all by something, or multiply it, scale it up, add a number to it to move it up or down. We've looked at this thing. So my equation for this, the most simple case is z is x squared plus y squared. Which means that this is r squared, and this is going to be z. Z is still a cylindrical coordinate, so it's not like I have to get rid of my z's. I just need to get rid of my x's and y's and turn them into r's and thetas. Well, I'm going to have x squared plus y squared is r squared. And so I'll say that this one is r equals the positive square root of z, which does make sense because, I'm only thinking about positive numbers and positive z's. All right, so that's a paraboloid. Next, I want to talk to you about a cone. So this one, let's see, I'm going to draw this one in a different color because this has got some straight lines to it, and I would not want to, be confused about the axes versus the actual cone itself. So I'm going to draw this one in, maybe I'll draw it in blue. Okay, so for the cone, this is going to be, all right, well, I'm just going to, that wasn't very good. Let's try that a little bit. That's better. Okay. And then I'm going to say that, that did a little erasing to make it look nice. Okay, and then I gave it an equation. Okay, so the equation for a cone, I think you could probably arrive to this if you really sat and thought about it for a second, but it's going to be z squared equals x squared plus y squared. Okay, and you think about it, the bigger that r gets, the bigger that z gets, right? Let's think about that for a second. But if you think about this, this is going to have kind of a symmetry to it that we could, replace z with negative z, and nothing would change on this. So really, this is a double cone. This is the type of cone that they talked about probably in an algebra class somewhere along the way, having, they gave you the conics, right? Something that we could cut into with a plane, and we could, get back a, a circle or an ellipse or a parabola or hyperbola. Okay, so again, if I've got z squared equals something that's looking like r squared, z squared equals r squared, then z could be r or z could be negative r. But I'm just going to say that r is equal to z because, for each of these cases, we end up tracing out the same image. And then the last couple I wanted to tell you about were just going to be some regular old-fashioned planes. I'll just do that pretty quick. One color. For a horizontal plane, say something like, please don't look bad. All right, that's all right. Okay, so this is the plane z equals c. Not my best work ever, but that's all right. Okay, well, if you think about it, z is a cylindrical coordinate as well, so I mean, it translates to z equals c. Okay, this is a horizontal plane. A vertical plane, on the other hand, and this is going to be tougher for me to vertical plane. Look at this. I sketched it once, but then I ended up kind of wishing I'd sketched it a different way. So yeah, this is where I'm going to actually put x and y in the foreground. I don't usually graph three-dimensionally like this, but I think that this is a situation where it would help. And then, how did I draw this? No, I didn't do it exactly like that. Pardon me. I'm going to just erase that. I did it, so I actually reversed x and y. Again, kind of just drew it like usual. Okay, so I've got, this is going to be my positive y-axis, and then this down here is going to be my positive x-axis. Yeah. And so what I'm saying is that this vertical plane that passes through the origin, what it's going to have is it's going to have like a theta value attached to it. So, say we're interested in theta equals, I don't know, pi over 4. That'll split this thing in half. It'll be, if you can envision this line in the xy plane and everything above it and below it, that's going to be our vertical plane. And so let's see, maybe I can draw this. It's not going to be a very wide plane, but that's okay. Let's see what I'm saying here. Oops. Okay, that's theta. Maybe I'll take out stuff you don't need to look at. Let's see, maybe I'll make that kind of like barely there. And I just don't think that was, I don't think I drew that right. Hold on, let me think about this. Yeah, this need to be a parallelogram like this. I don't know. It's getting worse as I draw more. But you can envision, if I took all of that away and just talked about that line, theta equals c, then we would have, and everything above it and below it, that would give us that would give us a vertical plane that passed through the origin. And I think that's all I've got to say about cylindrical coordinates. This is the system so that, maybe you're sitting and you're about to work some integrals that need to be changed into cylindrical coordinates. That's why I recorded this video, is to help you with that.